Welcome to this scientific lecture on droplet templating. Today we'll explore how emulsions serve as dynamic scaffolds to create porous solids, functional beads, and hierarchical materials through the elegant interplay of fluid physics and chemistry. Before we dive deep, let's establish our foundation. What exactly is droplet templating? Droplet templating is a bottom-up fabrication technique where emulsion droplets act as sacrificial templates. These droplets define void spaces or structural motifs in the final material. Recall that emulsions are thermodynamically metastable dispersions of one immiscible liquid within another, stabilized by surfactants or particles. Here we visualize an oil and water emulsion. The blue spheres represent oil droplets dispersed throughout the continuous aqueous phase. Each droplet is a potential template for material architecture. The critical challenge is to kinetically trap the droplet arrangement before thermodynamic coalescence destroys the structure. This is where polymerization, gelation, and drying come into play. Let's examine our first mechanism, polymerization-based droplet templating. This approach uses chemical cross-linking to preserve droplet architecture. In this method, monomers or oligomers are dissolved in the continuous phase. Upon initiation, polymerization occurs around the droplet templates, creating a solid matrix. Visualize the polymer network forming between template droplets. The green lines represent cross-linked polymer chains that grow around the red droplet templates, creating interconnected pores. Once polymerization is complete, the template droplets are removed through solvent extraction or evaporation, leaving behind a porous polymer monolith with controlled void architecture. Let's ask a critical question. What parameters control the final pore size in droplet-templated materials? The answer involves three key factors. First, the droplet size distribution, which is controlled by emulsification energy and surfactant type. Second, the volume fraction of the dispersed phase. And third, the stabilization mechanism against coalescence. This histogram illustrates a typical droplet size distribution in an emulsion. The x-axis represents droplet diameter in micrometers, while the y-axis shows frequency. Notice the distribution is not monodisperse, but follows a characteristic pattern. We quantify droplet size using the Sauter mean diameter, D32, defined as the ratio of the sum of n sub I times d sub I cubed to the sum of n sub I times d sub I squared. This weighted average is particularly relevant for surface area dependent processes. Now let's explore our second mechanism, gelation-based droplet templating. This method exploits sol-gel transitions to lock in structure. Unlike polymerization, gelation involves the formation of three-dimensional networks through physical or chemical bonds, without necessarily forming new covalent polymer chains. Think of silica sol-gel chemistry or alginate ionotropic gelation. In aqueous, continuous phases, colloidal silica nanoparticles or biopolymers like alginate can be induced to gel. The droplet interfaces often serve as nucleation sites for network formation. Here we see gelation occurring around droplet templates. The yellow spheres are the emulsion droplets, while the small red dots represent gelating particles or polymer segments that form a continuous network throughout the continuous phase. The gelation time, tau gel, is proportional to the ratio of initial viscosity, eta 0, to the plateau modulus, G0. This relationship is crucial for timing the templating process before droplet coalescence. Let's consider another important question. Why might gelation be advantageous compared to polymerization for certain applications? Gelation often proceeds under milder conditions without toxic initiators or high temperatures. Many gelation processes are reversible, allowing for template removal without harsh solvents. This is particularly important for biomedical scaffolds, where biocompatibility is paramount. Our third mechanism is drying-induced templating, where controlled evaporation drives structure formation. This is an elegant example of how non-equilibrium thermodynamics shapes materials. As the continuous phase evaporates, the volume fraction of droplets increases dramatically. This can drive a transition from a disordered liquid-like state to an ordered crystalline or random close-packed arrangement. This diagram shows the drying process. On the left, we have a dilute emulsion with dispersed droplets. As solvent evaporates, shown by the arrow, droplets become increasingly concentrated, and may adopt ordered packing arrangements on the right. During drying, capillary forces at minutiae can become significant, potentially deforming soft droplets. This introduces an additional level of structural control but also complexity. The capillary pressure, P-cap, equals 2 gamma over R, where gamma is the interfacial tension and R is the radius of curvature. For small droplets, these pressures can reach several kilopascals, sufficient to deform soft interfaces. Now let's discuss how these mechanisms combine to create hierarchical porous materials with multiple length scales of porosity. This is where droplet templating truly shines. Hierarchical porosity can be achieved by combining macroscale droplet templates with mesoscale or nanoscale porosity from the matrix material ITS. For example, emulsion droplets create macropores while nanoparticle packing creates mesopores. This schematic illustrates hierarchical porosity. The large red circles represent macropores, templated by emulsion droplets. The small green dots within the solid matrix represent mesopores from nanoparticle packing or intrinsic polymer porosity. Double emulsions, such as water and oil in water systems, allow even more sophisticated architectures. The inner water droplets can template internal cavities within beads, templated by the outer oil droplets. Here's a double emulsion droplet. The blue shell is the oil phase, containing multiple inner water droplets shown in white. This structure templates hollow beads with internal void spaces, ideal for encapsulation applications. Let's explore practical applications. First, advanced filtration membranes. Droplet-templated membranes offer tunable pore sizes and high porosity for separation processes. Membranes templated from high internal phase emulsions, or HYPEs, exhibit interconnected macropores that minimize hydraulic resistance, allowing high flux at moderate driving pressures. This graph shows flux versus applied pressure for a droplet-templated membrane. Notice the linear relationship, indicating efficient Darcy flow through the interconnected pore network. High-porosity materials show steeper slopes. The flux, J, follows Darcy's law. J equals K delta P over mu L, where K is permeability, delta P is pressure drop, mu is viscosity, and L is membrane thickness. Droplet templating allows independent control of K through pore size and connectivity. Our second application is tissue engineering scaffolds. Here, biocompatibility and controlled degradation are as important as structure. For tissue engineering, pore sizes between 100 and 500 micrometers are optimal for cell infiltration, nutrient transport, and vascularization. Droplet templating provides precise control in this range. Using biocompatible polymers like alginate chitosan or polyethylene glycol, droplet-templated scaffolds can mimic the mechanical properties and biochemical cues of natural extracellular matrix. This diagram shows a scaffold cross-section. The red circles are interconnected pores templated by emulsion droplets. The green triangles represent cells that have infiltrated the scaffold, adhering to pore walls and proliferating. An important question arises. How do we control the degradation kinetics of these scaffolds to match tissue regeneration rates? The answer lies in careful material design. We can tune degradation through polymer chemistry, selecting hydrolytically or enzymatically degradable linkages. Cross-link density affects water uptake and swelling, and molecular weight between cross-links determines mechanical stability. Empirically, degradation time, T-deg, scales approximately as molecular weight to the 1.5 power. This allows predictable design of scaffolds that degrade over days, weeks, or months. Our third application is catalyst supports. High surface area and controlled mass transport make droplet-templated materials ideal for catalysis. In catalysis, we often face a trade-off between surface area and mass transport. Droplet-templated supports with hierarchical porosity solve this problem. Macropores allow rapid reactant access, while mesopores provide high surface area for catalyst deposition. This schematic shows a catalytic support. Yellow circles are macropores providing transport channels. Red dots on pore walls are catalyst nanoparticles with high surface area. The blue arrow indicates reactant flow through the interconnected pore network. Catalyst immobilization is straightforward. Metal nanoparticles can be deposited via impregnation or in situ reduction. Enzymes can be covalently attached or physically adsorbed, depending on application requirements. This kinetic curve shows conversion versus time for a catalytic reaction using a droplet-templated support. The curve exhibits excellent activity with minimal mass transfer limitations due to the hierarchical pore structure. Let's return to fundamentals and examine how fluid physics governs the entire templating process. Understanding these principles allows rational material design. Interfacial tension, gamma, is the dominant force at small length scales. It dictates droplet sphericity and resistance to coalescence. Surfactants lower gamma, stabilizing smaller droplets. Surface tension decreases with surfactant coverage according to the Gibbs adsorption equation. Gamma equals gamma 0 times 1 minus gamma over gamma infinity, where gamma is surface excess concentration and gamma infinity is saturation coverage. When droplets approach, the intervening continuous phase film must drain. The drainage time determines whether droplets coalesce or remain stable. This is described by Reynolds lubrication theory. Drainage time, T drain, is proportional to viscosity, eta times droplet radius r squared, divided by interfacial tension gamma and critical film thickness h sub circa. High viscosity and low interfacial tension, slow coalescence. Here we visualize two approaching droplets. The yellow region between them is the draining film of continuous phase. Red arrows indicate drainage direction. If drainage is too fast, coalescence occurs. If slow enough, the structure can be kinetically trapped. This raises an important practical question. Can we predict the optimal emulsification conditions to achieve a target droplet size distribution? Yes, through dimensionless analysis. The Weber number, which compares inertial to interfacial forces, is particularly useful. By controlling Weber number through mixing speed and surfactant concentration, we can target specific droplet sizes. The Weber number, WE, equals RHO versus squared L over gamma, where ρ is density, V is velocity, L is characteristic length, and gamma is interfacial tension. Higher Weber numbers produce smaller droplets. For ultimate control over droplet size and uniformity, microfluidic techniques offer unprecedented precision. This represents the cutting edge of droplet templating. Microfluidic flow focusing, or T-junction geometries, generate droplets with size distributions often below 5% coefficient of variation. This monodispersity translates directly to uniform pore sizes in templated materials. This schematic shows a microfluidic T-junction. The red arrow indicates dispersed phase flow from above, the green arrow shows continuous phase flow from the left. At the junction, uniform droplets form and flow to the right, shown as cyan spheres. Droplet diameter, d, is proportional to the ratio of dispersed flow rate qd to continuous flow rate qc, multiplied by channel width w. This simple relationship allows precise diameter control through flow rates. After synthesis, rigorous characterization is essential to verify structure and properties. Let's discuss key characterization techniques. Mercury intrusion porosimetry applies increasing pressure to force mercury into pores. The pressure required is inversely related to pore size through the Washburn equation, yielding a complete pore size distribution. The Brunauer-Emmett-Teller method uses nitrogen adsorption isotherms to calculate specific surface area. High surface areas, often exceeding 100 square meters per gram, are characteristic of successful droplet-templated materials. This pore size distribution from mercury porosimetry shows differential pore volume versus pore diameter. The sharp peak indicates narrow size distribution from monodisperse droplet templates, a hallmark of high-quality droplet-templated materials. As we conclude, let's look toward future directions. Droplet templating continues to evolve with new applications emerging regularly. Four-dimensional printing incorporates time as the fourth dimension. Using stimuli-responsive emulsions that change droplet size with temperature or pH, we can create materials that dynamically restructure their porosity in response to environmental triggers. Nature employs hierarchical structures extensively, from bone to wood. Droplet templating combined with biological assembly principles offers pathways to synthetic biomimetic materials with unprecedented properties. In energy storage and conversion, droplet-templated electrodes provide continuous electron and ion transport pathways. High porosity reduces tortuosity, improving rate capability in batteries and enhancing mass transport in fuel cells. This summary diagram illustrates the complete, droplet templating paradigm. Starting from emulsion science on the left, we apply polymerization, gelation, or drying mechanisms shown in green. These pathways, indicated by red arrows, lead to our three main application categories: filters, scaffolds, and catalysts. Let's summarize the key principles we've explored in this lecture. Emulsions offer exquisite control over structure through fluid physics. Droplet size, volume fraction, and spatial arrangement directly determine final material architecture. The critical step is kinetic trapping before thermodynamic coalescence. Whether through polymerization, gelation, or drying, we must lock in structure faster than it can relax. By combining droplet templates with intrinsic material porosity, or using double emulsions, we achieve hierarchical structures that outperform single-scale architectures. The versatility of droplet templating enables diverse applications. Each application leverages specific aspects: high flux for filtration, biocompatibility for tissue engineering, high surface area for catalysis. Understanding interfacial tension, coalescence dynamics, and dimensionless numbers allows predictive design rather than empirical trial and error. Modern tools like microfluidic droplet generation and comprehensive porosimetry ensure we can both create and verify the intended structures with high fidelity. Droplet templating represents a beautiful convergence of fluid mechanics, colloid science, polymer chemistry, and materials engineering. By harnessing the self-assembly of emulsions and judiciously applying chemical or physical transformations, we create functional materials whose architecture is dictated entirely by fluid physics principles. As we continue to refine our understanding and control, the future promises even more sophisticated materials with unprecedented performance. Thank you for joining this exploration of droplet templating science.